My street was plowed, but done
Oh,
poorly.
this morning?
Yeah.
I was talking about yesterday, like.
You know, yesterday was easier for me.
Yeah, I had to push my neighbor into their driveway.
I got stuck in my.
No. Getting out
Today?
this morning.
We almost snowballed it.
I just turned.
And so we just like shoveled it all to the side. I needs a better. No, it
I
was
don't have a
slick.
snowblower either.
I don't either.
Hey, wait, who's the better driver?
Me. It actually is. No, it actually is me. My mom's upset. That's my mom. He's a terrible driver.
Got my mother's stamp of approval.
My mommy says
Just
so.
because I drive too fast, I can't drive. I drive fast too. The other day I was going really, really fast, and I was like, "It was Benjamin driving." I'm like, "No," and she's like, "Really? I could have sworn that was your brother." I'm like, "Well, I guess I'm not working."
All right.
Alright, moving on. Homework.
That was a good story.
Alright, so far we have described our equilibrium really with just concentrations of gases. We're going to talk about a few other things today. There's a relationship between the pressure and the concentration of a gas, seen with an amazing equation that you guys all should be fairly familiar with. If I say gas law, what is the first gas law that comes to your mind?
Ideal gas.
All right, that's good. The ideal gas law.
But that's where it hits right here anyway.
PV equals nRT. Now, you should remember from last semester that we did do equilibrium expressions when we used gas pressures. Do you guys remember, at least vaguely, doing that? We called it KP. Okay, where we had Kp equals, and then you had the pressure of a gas squared, or the pressure of the gas cubed, depending upon what the coefficients were.
Yeah.
We did that last year. It wasn't something we spend a whole bunch of time on, but there is a relationship between concentration and pressure using the ideal gas law. Okay, so how would we get concentration from the ideal gas law? Any idea?
It's you divide by V. Sorry. It's mole per volume. So you divide by V.
Okay, yep. So what concentration is mole divided by volume. So I could take and have pressure equal
N over V.
nRT over V, but what is N divided by V? Concentration. So there's a relationship between the pressure of a gas and concentration. We're going to show that today. I'm actually going to do some derivations. So hopefully you will appreciate it. We'll see. But before I do that, I do want to show you the next slide. So this is just taking and replacing N divided by V with concentration C, and that's where that comes into play. Most of the time when I just put the constant K, I'm referring to Kc. So yesterday when we did our equilibrium expressions, we just put K, and we had the concentrations of product over reactants, correct? Okay, so when you see just K, we're assuming we're dealing with just the concentration equilibrium expression. All right? I will probably never write Kc. However, Kp is a constant when you use pressure in the equilibrium expression. Now, I will show you there's a relationship between K and Kp. Sometimes they're equal, but not always. And I'm going to show you the relationship with an equation that I'm going to derive here. What I want you to do before I show you the relationship between Kp and K is I want you to do the Kp expression. Well, I'll just show it to you since I haven't shown it to you. It's really just like your K, just instead of using concentrations, you're going to use the pressure values. So if I look up here, I've got my gases, my one product. I would just say pressure of NaCl raised to the second power because of the coefficient. Really not any different except for I'm using pressure instead of concentration. okay? Divided by my reactance, pressure of NO, raised to the second power. I could put parentheses around to show that I'm multiplying. And pressure of Cl2. I want you guys to find the Kp of this. Shouldn't take you very long. Go ahead, get you moving a little bit, because I'm going to do quite a bit of writing on the board here in a little bit, and I don't want you, be wandering off into la la land.
Here.
What? I thought it was 920. Yeah, 8.9 times 10 to the third.
Yes, I was saying it's a roaring number, 1920s. Roaring 20s, never mind. 1920.
I thought you were a very illiterate person.
Yeah. Sorry.
What's the matter?
All of our marbles are missing.
That's cool. Yeah.
I lied.
Does it always have to be in
Okay.
As long as the units are the same, it shouldn't matter. Okay? Any questions on this? And I'm going to show you the, like I said, in a second, I'm going to derive the relationship between K and Kp. They serve the same purpose, though.
Are they unitless as well?
Yeah, they are also unitless as well. Okay? So I think, before I show you this, even though technically if you plugged in the atmospheres, they would not fully cancel out. This is just going to be considered a unitless guy. Now, let me show you. I'm going to use this kind of generic equation that we've been dealing with thus far. Now, you do have space above where you just wrote if you want to write this in. You don't need to necessarily. That probably means none of you will, but. Okay? What I'm going to do here is I'm going to show you how Kp and K are related. Sometimes they actually do just equal each other, but not always. So if I were to write the equilibrium expression of this, it'd be pretty easy. Like that, yeah? Right? Then we just talked about how there's a gas law that actually has concentration embedded into it. And if we solve for concentration in that particular gas law, what we get is pressure divided by RT. Okay, that's the equation I just had on the board earlier. Okay? Now, if these represent the concentrations, could I take and substitute this version of the gas law into this? Could. Do it. So what we get is P of NH3 over RT, and that whole thing is squared over your pressure of your N2 over RT, pressure of H2. Woo!
You set it up on the sides.
Over RT. And that is cubed. following what I did? What?
Yeah.
Yep. Okay. Now what I'm going to do is I'm going to pull out the pressures so that I can simplify the 1 over RTs. That make sense?
I'm sure it will once you do it. Charlie, I don't understand what
Let me see what I did.
Oh, that one didn't even explode. Why do you always grab it?
Everybody see what I just did? I just factored out the pressures. Could I multiply that back through and get to the exact same thing?
Yeah.
Yes. Okay? What does this look like?
I think you already solved for it.
What can I replace with that?
Then the answer you already got.
What do you mean the answer I already got? I haven't got an answer for this yet. What can I replace with that? KP. So, what we have is K equals KP times, can we simplify this? What would it look like? So it would be 1 over RT to the 4th, 1 over RT to the 2nd, so it would be 1 over RT to the negative 2nd.
The power would depend on the exponent, right?
What did you say?
But the exponent would depend on
Yes. Yep. So really what we have is RT to the 2nd, because what we had is 1 over RT to the negative 2nd. We can bring the RT up, flip the sign, and we'll get RT to the 2nd. So in this particular case, here's the relationship between K and KP. Now, it's also dependent upon the exponents. For example, if I had something like this, H2 plus F2 equals HF. 2HF, excuse me. Do you see how if I add the coefficients of reactants? Yes.
Do you want
Does anybody like Mountain Dew? Anybody want Mountain Dew? Thanks.
Thank you.
What you see is the sum of my coefficients here equal the sum of my coefficients there. So what would happen is you would have 1 over RT squared and 1 over RT times 1 over RT, which would make 1 over RT squared. So the top and the bottom for 1 over RT would what? Cancel. And in that case, your K would just equal your KP. So, it is dependent then on the number of gas or coefficient particles that you have. So here is the simplified version. It's what we got from the derivation. Okay, and that's really what the purpose of a derivation is to show you, okay, great, I'm glad that this is the equation, but where did that come from mathematically? Now, I've learned as I've gotten older to kind of appreciate that. When I was younger, I kind of just thought, well, I don't really care why or how. Just show me the equation, let me do it. Would you agree with that most of the time? Yeah, but I don't know, maybe just as you get older, you just start to be more curious about some of these things. I don't know. So, take it or leave it if you enjoy that or not. Just kind of showing you where that came from and how they're related. Now, this is really important because what you have here is the sum of the products minus the sum of the reactants. So could you get a negative change in n? You could. Okay? It's very possible. So, let's do this guy. It says using the value of Kp, which you solved for the Kp in the previous problem that we did. Okay, so it's saying using that Kp, obtain, oh wait, did it just give it to you again? Okay. Here it is, but this is what you got in your previous problem, right? I believe, 1.9 times 10 to the third.
Yeah.
Okay? So calculate the K for this particular guy.
For that.
Yep. Based on the previous slide, where I just gave you that, after I derived it, where we got that equation, use that to calculate the K value. Kp and K do not equal each other in this case.
What's R?
Oh, good question. The R is going to be your gas law.
0.0.
You don't remember it? 0.0820217. Technically 206, but we'll just go 0.0821. Does it make sense why it would be your gas law constant?
Did that mean solid?
Yep. Yep. Good catch. Sometimes we get into doing all these equilibrium stuff and into all the math stuff and forget the conceptual stuff. What is going on when you're at equilibrium? Okay, the rate of the forward is equal to the rate of the reverse. What was the book definition of when equilibrium is? Remember?
Concentration ceases to change.
Yeah. And they used a different word. They said when the concentrations of your reactants and products are constant. Now that doesn't mean equal. Remember we talked about how it doesn't necessarily mean they have the same concentrations. When they say constant, they just mean they're not changing anymore. Okay? So, what do you guys get? 4.6 times 10 to the fourth? It's possible. I used the R, that's 0.08206 instead of 0.081. I probably should have added you 0.06 because I think that's what it's supposed to be. Not rounded. You're still working. Or you could just raise it to the exponent of -1. Yeah, so what you could really just do is multiply them all. So it's K equals Kp RT to the -1, right? Is that what you got? Okay, so when you divide to find Kp, wait.
No, it's Kp equals.
Sorry, I messed that up, you're right. Kp equals K. So when you want to solve for K, you're dividing by RT to the -1. Well, you can bring that up and remove the negative exponent. So really, it's just K equals Kp RT. Does that make sense? Okay. 4.6 times 10 to the fourth?
I don't know what.
Still?
It gave you Kp, right?
Yep. So you should take that 1.9 times 10 to the third.
And then third, that's what I did wrong, I have -3rd.
Alright. Here's, again, also, what?
Let's look at like 77.7. So it should be, those numbers, those two all apply to the negative first time?
No, not to the negative first. So, do you not see that it was Kp equals K RT to the negative 1?
Yeah.
Right, but we're solving for K. So I would divide by RT, and then I can bring it
I
up.
had the equation wrong, that's why I had.
Yeah, I messed it up the first time too, so
That's
it's.
why it's, okay.
Yep.
It's not that.
Okay.
Kp equals K.
Now, in these next two things, this should also be a little bit of review, so that I can tell you guys are fully aware that this is review, right, Amy?
Yeah.
Okay. Heterogeneous versus homogeneous. You already know what hetero and homo is, so I'm not going to get super crazy into reminding you what hetero and homo is. Same phase, different phase. At this point, we've kind of just assumed that everything was in the gas phase. So I don't know if you guys remember or not that there are a couple guys, when you put it in your equilibrium expression, don't do anything, and so we just remove them. Do you remember what those are?
Spectated.
Good guess though.
Intermediates.
No.
We can use that.
Okay, you maybe don't remember this little subtlety, but when you're writing the equilibrium expressions, you only put in gases and aqueous. You do not put in solids or liquids. I don't know if you remember that.
Yeah, I do.
Okay? You're probably wondering, well, why is that? I did a little bit of research this morning because I knew kind of why, but I wanted to refresh my memory on why. It has to do with this. Okay? So if I'm doing an equilibrium expression, I've got, let's say, that doesn't make any sense. It's going to be products over reactants. Okay? You're going to get a constant. Okay? And the big thing that we have to think about is, can the concentrations change or not? For example, if C's concentration could not change, would it affect K? No. It could essentially be absorbed into the constant. For example, if this was a constant, couldn't I divide by that? And wouldn't a constant divided by a constant give you another constant? So let me explain why solids and liquids aren't put into the equilibrium expression. Okay, or maybe why, maybe I should start by saying why gases and aqueuses do. Okay, yes, yep. Essentially the reason why gases and aqueous can change is because gases can be compressed or expanded. That would change its what? Density, and then therefore changes concentration, right? Does that make sense?
Yeah.
Okay? We all know that things that are dissolved in water, I could dissolve more or I could dissolve less, right? Essentially changing its concentration. Okay? Well, solids and liquids, you cannot change their concentration. Any ideas why you can't change the concentration of a solid or a liquid?
Atoms are held tightly.
Yeah.
They can't be compressed,
Yeah.
right? So even if I take a bunch out, I still have the same density, I still have the same concentration per unit volume, right? Okay? 2 moles is going to occupy twice the volume as 1 mole is, right? So the concentration is the same. So essentially what they do is they take it completely out because it's just a constant, it never will change, and so really it gets absorbed by this constant. What they say is if this is a solid, they divide over here, and a constant divided by a constant is just another constant, so let's absorb it into our constant. Does that make sense? Okay? So that's kind of the quick version as to why solids and liquids aren't seen in the equilibrium expression, because you cannot change the concentration at all, and so why even worry about putting it in there then? So, last thing, make good time today. Oh wow, I want K and KP. Oh, okay. You're going to have to write the equations out before you do K and KP. Again, giving you some more practice at this. What I will say about B, you probably aren't familiar or have never seen something like this, copper 2 sulfate pentahydrate. What that is copper sulfate that has a certain amount of water molecules that are absorbed in it, or are in its chemical structure. So this is what it actually looks like. This is how you would write that. So you should be able to write the second part of that and do, yep. Because technically this and this are one structure. And so instead of putting, you know, it's not like it, I'm not 100% sure if it's actually chemically reacted or if it's trapped inside the solid. I think it's more trapped inside the copper sulfate solid. And so since it's not chemically infused, they don't put it together. But I'm not 100% sure on that. And that's why it says, is heated to drive off the water vapor that was in your pentahydrate. And so really what you end up with here, and this is going to be liquid.
Oh, you're right.
Yeah, maybe I'll just do this with you. So this whole thing is in the liquid state, so that should help you out on that.
Oh, it's already down. Great.
So basically what this is just driving off your water molecules. So it ends up being a pretty easy equilibrium expression to write. So I want you to then do A as well. Take a look up. I can't remember if hydrates are actually chemically infused or they might be. Does everybody understand what this question's asking?
Just the expression.
Yeah.
Not find the value.
Yep. Just write the K and KP expressions, and again, they're not going to be that different. The only difference between them is P versus concentration. Still have the exponents are come from their coefficients. However, these are heterogeneous guys, so gotta remember that. The ideal gas law song day. Uh-huh. I really hate that day. But I love it at the same time. You know, it's a love-hate relationship.
Love relationship with cheesy YouTube song.
Thanks. Thanks. Glad you're glad for me. So what did you get? Still working? You're not sure what you're doing?
No.
I-
Oh, I did that one.
You're not sure how to write the equation, or?
I'm not sure they're right.
Okay.
That way of saying it.
Solid phosphorus pentachloride, what is that?
It's not you right in. It's solid.
Sure, okay.
It's
Yeah.
KCl5.
KCl5,
Phosphorus.
PCl5.
Yes, you're right. I'm thinking potassium. I don't know why. No.
I'm glad for you. I'm kidding, right? Alright, equals what? As a,
Think they passing bond that way.
now it's already balanced, so then it should be easy to write the equilibrium expression, K equals concentration of CO2. Your Kp would be Kp equals pressure of the CO2.
Is that all it is?
Are you guys all waiting for me to just do that?
Yeah.
Wait,
I only
No,
know.
I actually did it.
wait, no.
What was the answer?
KP
Is it that hard to do? You guys don't know how to write it, or are you just lazy?
No, I did it.
Guess I was
I was looking
overthinking.
at you.
You mean the same answer.
Like,
Like if you were to solve for them?
no. Like, what are the answers?
You mean the ones I just said a second ago?
Yeah.
K equals the concentration of CO2. Kp equals the pressure of CO2.
There's just no concentration.
And we'll write it down. Okay. Equals that. Kp equals that. So, for the second guy, K is going to be equal to that, to the fifth power. Kp is going to equal the pressure of that to the fifth power.
How do you do the pressure to the power? Write it. Is it still?
You can put parentheses around it if you want to. Stop parentheses.
We keep keys though, right?
Yeah. Sorry.
Oh, okay, okay. Okay.
Yep. Makes sense? Okay, tomorrow is the fun math day. We get to learn about our ice tables tomorrow.